A specific way of obfuscating traffic is to use what's called a covert channel, encoding that traffic that you wish to hide in the form of some other traffic. Covert channels abound. Pretty much anything that emits bits could be used as a covert channel if you can figure out a way to perturb it to generate the encoding. The challenges are finding covert channels that are both hard to detect and high bandwidth. A related topic is steganography, or the practice of hiding information in other so-called cover content or cover media. We'll explore both of these concepts next. In general, the goal of steganography is to hide the existence of any communication. A common way of doing so is to make one form of traffic look like another, or to hide one type of content in another. The motivation behind steganography, or more broadly, information hiding, is that sometimes, even if traffic is encrypted, the mere existence or presence of a communication channel might be enough to incriminate a user, and that channel can also be subject to interference or blocking. We saw that particular motivation in the past module when we talked about Tor and pluggable transports. In that case, if a sensor is able to detect Tor traffic, then it doesn't necessarily need to know the contents or the nature of that communication. It can simply use its knowledge that the traffic is Tor traffic to incriminate a user or disrupt the communication. And so hiding the existence of that communication can sometimes be useful. In thinking about steganography or information hiding, we can talk about a number of different properties that we might like to achieve. In particular, client deniability, the property that the client or the user of that software can deny that it's using it. That deniability could be deterministic, or it could be statistical. In other words, a sensor might have no way of knowing that a client was using a particular piece of software, and you might need that kind of strong guarantee. But in some cases, you might need an even stronger guarantee that says the sensor can't even suspect that you might be using that piece of software. One can also talk about covertness or deniability on the server side. In other words, the proxy or the other end of the connection should be able to conceal the fact that it is participating in this circumvention protocol. Otherwise, it too might be blocked. Another potentially desirable property is robustness of the communication channel. This is where making it difficult to detect the communication can be useful, because if the sensor can't detect that the communication is taking place, then perhaps it can also make it more difficult. Then in some cases, that also makes it more difficult to disrupt the communication. And of course, we'd like it to perform well as well, otherwise nobody's actually going to use it. Here's an example of image steganography, where a message is hidden in the image on the right. This particular example was implemented using a tool called Outguess. One of these images, as I mentioned, the image on the right has embedded content, but you actually can't tell, and that's exactly the point. We first deployed this type of covert channel in a system called Infranet back in 2001. In this particular setup, the idea was to encode or embed or hide web requests in other web requests, and hide web responses in other web responses. A client, or a so-called requester, would send a sequence of web requests to a forwarder, which could then forward those same requests or link numbers to a responder that could decode that particular sequence into a string that corresponded to a URL. That responder could then fetch the content corresponding to that URL and return the content. Except it wouldn't return the content in raw form. It would use something like image steganography to embed the content in another image and subsequently return that cover traffic to the requester via the forwarder. The sensor would see traffic that would be apparently destined for a forwarder or a responder, but in fact was intended to request web traffic. It was intended to request content from other servers on the internet. The traffic would thus look innocuous to the sensor, even though the request was for censored content. The basic Infernet architecture simply had a requester and a responder pair. An enhancement to the protocol adds a forwarder in the event that we need to actually have a smaller number of trusted responders. Receiving content on the downstream is easier because web traffic is asymmetric, and so other content can be embedded in larger cover traffic like images or even videos. Encoding upstream requests is actually harder because there's less cover traffic. The cover traffic itself are simply HTTP requests. Fortunately, the message that we need to encode is also smaller. The way that Infernet implements this type of encoding is by encoding messages with a sequence of web requests. And so the order in which those requests are issued itself encodes another URL. It's easiest to understand this with the toy example. A responder might send to the requester a dictionary that says if you make a request for link 1 on a page, that means a particular website. For link 2, that means another website, and so forth. That, of course, has a number of drawbacks. In particular, in general, there are an infinite number of possible requests, and it's impossible to send a dictionary that captures every possible URL. There's another drawback to this approach is that we'd like that initial sequence of web requests to also look normal. If that observable sequence of web requests looks like someone just requesting random web pages or random links on a page, then that itself might also be suspicious. And so the design of Infernet extends this basic idea using a particular style of dictionary that both makes the requests more efficient, allows for the encoding of arbitrary URLs, and does that mapping in such a way that the sequence of visible requests tend to look more innocuous. We might also ask whether we can do this without dedicated infrastructure. The Infernet setup requires having dedicated forwarders and responders. The rise of user-generated content sites can help in some regard because they can provide some infrastructure if we could only figure out how to use them. Subsequently, we designed a system called Collage that works similarly in spirit to Infernet, but uses user-generated content sites as essentially drop sites for requests and responses. So instead of exchanging messages directly or through a responder, Bob might steganographically embed a message in an image or a video and post it to a user-generated content site, such as a photo sharing site or a video sharing site. Alice could fetch the corresponding content that Bob posts, which to an observer might look like photos from Bob's latest vacation or cat videos. In fact, Alice isn't interested in the content that Bob overtly posts, but rather in a message that Bob hides using steganographic encoding in the images or videos. Once retrieving that content, Alice can then extract the message she really wants from Bob. In some ways, this extends Infernet and overcomes some of the limitations. It's robust. You can use redundant user-generated content sites to post content in multiple locations. Users generate purely innocuous-looking traffic simply by browsing content on user-generated content sites. And there's no dedicated infrastructure required. Here's how that works step by step. Alice wants to obtain a message from Bob. She picks the message identifier corresponding to that message. In the case of a website, that might be a URL. Only the intended recipient should know that particular URL or identifier. Upon needing to return that content to Alice, Bob obtains some cover media, such as an image, embeds that message in the cover, uploads that cover to a user-generated content site. Alice then somehow finds that cover media, downloads it, and then decodes that message from the user-generated content site. Of course, crawling all of a user-generated site isn't an option, and so Alice and Bob need to agree on a subset of content where this information might be hosted without any immediate communication. So there needs to be a predictable way of mapping those message identifiers to subsets of content that's hosted on these user-generated content sites. The solution that we use in the particular case of Collage is called task mapping. Here, a message identifier such as a URL is hashed and placed in a corresponding ID space. The identifier is thus mapped to nearby tasks in that ID space, and the task IDs correspond to specific tasks that Alice can perform to retrieve the content corresponding to that message identifier. A task might be search for blue flowers on Flickr or look at John Doe's videos on YouTube. Receivers perform those tasks to get the vectors or cover images, and senders can publish vectors into this identifier space so that when receivers perform tasks, they get the vectors corresponding to the content that corresponds to the message ID. All of these systems face the challenge that they need to mimic what's supposed to seem like normal behavior. And that can be very difficult because internet protocols are complex, and completely implementing and mimicking a protocol, including how it would behave under all possible conditions and corner cases, is rather difficult. Complex interdependencies between subprotocols, behavior under error or malfunction, bugs in specific versions of software, and even user behavior can introduce vagaries that create distinctions between a true protocol and a covert channel that's trying to mimic the actual protocol. These divergences can be exploited by sensors to actively detect and distinguish various covert channels. For this reason, it's often said that these types of systems can be very difficult to implement and deploy in practice, because faithfully parroting a protocol is in fact much more challenging and difficult than simply implementing the protocol itself. In fact, there's a paper called "The Parrot is Dead," where you can read more about this particular phenomenon. In summary, information hiding techniques such as steganography and covert channels can be used to evade censorship detection and blocking. However, these techniques often have quirks that make them detectable because they perturb the original content or they don't behave like the original protocol. They also typically introduce very high performance overhead and thus are often most useful for bootstrapping an initial connection or handshake to some other circumvention tool that's much higher bandwidth. In particular, the design of high bandwidth covert channels and transports remains an active area of research.